was heading down at that point. Do you still have a follow-up question, or?
I don't have a question.
You might have just erased something off of it.
Say it again?
I think you might have erased something off of your equation.
I would not be surprised. Oh, yeah, I did. There we go. All right, if that's my velocity, as we did last time, my acceleration would be negative a omega squared sine, not sine, cosine of omega t plus phi. That is my maximum acceleration. So if A max is a omega squared, that would also be equal to F max over over my mass. Acceleration being force divided by mass. Omega is the square root of k over m, so that becomes like amplitude times k over m is equal to F over m. My masses cancel out, and what I'm left with is my maximum force happens at the amplitude times the spring constant, which comes straight from Hooke's law. The fact that the force is directly proportional to the displacement. So when I'm at my amplitude, I have the maximum force acting on this thing. And again, two ways to find acceleration. Questions to hear?
How did you go from velocity to a times k over
From what we did last week, if that's my position formula or my displacement formula, that's my velocity formula, and that's the acceleration
No,
formula.
I'm like on that bottom part right there.
How to get to here?
Yeah.
I know that my maximum acceleration is the amplitude here, so a omega squared. Omega, as we derived last week, is the square root of k over m. So omega squared is k over m. So it's a times k over m. That's where this comes from.
Okay.
And then that's just the second law.
Yeah, I got it.
Okay. All right, I know what you're thinking now. You're thinking, all this stuff is great, but could we possibly apply this to a different situation? And something besides a spring? Well, you're in luck.
Couldn't you do it with somebody like jumping as high as they can? Or bicycle's gonna fly?
They're on a pogo stick, would it work?
You got the spring in there, so you probably could do pogo stick. If you're just jumping, you could. The trouble is you have two different sort of things going on. Once you're in the air, it's like a free fall problem, so it can't really be modeled by simple harmonic motion. While I'm bouncing up and down, you probably could model it. Actually, if you take the world, and if you could dig a hole straight through the middle. So if I then stepped into the hole, I would go shooting, assuming I don't burn up. I go shooting down to the other end, I'd pop out, my feet would pop out on the other end, and then I'd come back, and that also is actually simple harmonic motion.
Just be a never-ending cycle.
Pardon?
Would it just be like a never-ending cycle going back? and
Yeah,
forth?
we're assuming no resistance.
So there would be no way for you to possibly fall like a meteor to outer space.
Wait, say it again?
So there'd be no possible conceivable way to jump through a hole in the earth that leads to the other side and fall like a meteor, like to the other side. Like
Well, you would get faster and faster and faster until you passed the middle, and then you'd slow down. And so, if I just stepped into the hole, then I would pop out on the other end. My head would basically be level with the hole. My feet would be 6 plus feet up in the air, and then I would go shooting back on to the other side.
Sounds like an effective torture method.
It
There's
takes
a-
45 minutes, I think.
There's a
Nice.
video on that, right?
Pardon?
There's a video on that probably, right?
I did a video on that, but I don't know if I posted that with 151. Someone else probably has done it.
So, a quarter of your period would be when you reach the middle
Yep.
of the earth for the first time?
Yes. And the reason why it works, why that simple harmonic motion, is all we need to do is find that some situation where the acceleration is somehow proportional to, or the negative acceleration to the displacement. And when you jump into the hole, so if I've got my planet here, where that's the radius of the planet, if I'm outside that planet, it's big G M1, M2 over R squared. It's a 1 over R squared relationship if I'm outside, but once I get within the radius of the planet, it's linear. It requires calculus to derive that, but when you're at the middle, there's no force acting on you. But we get position, how far you are away is directly related to the force and therefore the acceleration.
If you drilled a hole in the middle of the earth, would you be able to survive like the force, like the speed you're going? Say you could like go through the core without the heat bothering you. Would you ever go too
I don't
fast?
think the fastest you would accelerate would be 1G. So, you know, if I stepped up on the table and jumped down, that's the greatest acceleration my body would experience. So I'm getting faster, but my acceleration is dropping off as I'm going this way. So that's not what would kill me. Probably in reality, it's not much reality what it would throw into it. Drilling the hole once we got to the molten core, that probably would kill more than anything else.
But ignoring like the core part, if there was an actual like tunnel,
You would,
You
the speed
could
would not
survive.
kill you, or the acceleration would not kill you.
okay.
Yeah, I'm trying to think, you black out at, well, it depends on how long it's sustained, but I think 3Gs sustained at 3Gs would be black out. And the most we can experience here is 1G. All right, so let's take a look at the pendulum. The simple one. In other words, the simple pendulum has a fulcrum. It has an ideal string, or this is ideal, in other words, massless. Mass is equal to 0 kilograms. Stretchless, etc. And the mass is all at the end, and this is a point mass. In other words, we're not worrying about the size of this. So as long as it is small compared to the length of the string, this is a reasonable assumption. That's some length L. So let's do an analysis just to see if it does obey Hooke's law, or what we will see is that under what situations does it obey Hooke's law. What are the forces acting on the mass?
Weight. Tension.
That's theta on there. When I let go, I pull it back and I let go, what is the direction of acceleration? Tangential acceleration, I should say. Or acceleration based on the change in speed. Because I will assure you, if I pull this back and I let go, it will start to move.
Perpendicular to the tension.
Yes. So it's going to accelerate in that way. There'll be tangential acceleration. But it's also traveling in an arc. So there's also going to be centripetal acceleration.
Why is it tangential to the accelerator, or why is it accelerating tangentially, perpendicularly to the tension?
This is gonna travel in an arc of radius L. It is going to be changing in speed and direction. We know it's gonna change in speed because if I pull it back and let go, it will go from 0 to something. So I know therefore it will change its speed, and the acceleration based on change in speed is tangential. It's gonna be tangent to the path. So while it's going that way, the acceleration's in that direction, and when it's over here, acceleration's in that direction. I feel like I didn't answer your question. Do you wanna try again?
No, I think I answered it.
Okay. So when I set up my coordinate axes, I'm gonna set them up. Fortunately, they're perpendicular to each other. So I'm gonna set them up in like that. We'll call it I hat, J hat. And will come out. Which means, what am I breaking up?
Wait.
Yes. I know this angle here is theta. That means this angle here would be the complement, so called theta prime. This is a right angle, so this angle here is theta. And if I'm breaking weight up, so if that's theta, this would be theta prime, and so that angle there would be theta. So if this is what I'm breaking up, that's my weight. The opposite side here is, so I've got my tension acting this way. That would be the weight, mg sine theta. And this would be mg cosine theta. Therefore, what are my two equations of motion? Go ahead.
Is it, f of t, or tension minus mg cosine theta equals, mass times centripetal acceleration?
Yep. And the other one?
Is it just mg sine theta equals mass times acceleration?
All right. I'm gonna put a little T there to emphasize that it's not the same as the other acceleration. The first equation, these are indeed the two equations of motion. It's the second one that I care about in terms of what we're talking about here. Mass cancels out, which is convenient. But I have acceleration here and theta. Now we do need to make one other adjustment. What is, and it's the thing that I usually forget. Recognize that this is equilibrium when it's straight down. I'm bringing it this way, and it's going to accelerate that way. There should be an extra negative sign in there, one side or the other. But I have a linear quantity and I have an angular quantity, and we need to somehow sync them. So what is the relationship between tangential acceleration and angular acceleration?
90 degrees.
Not 90 degrees, looking for a formula.
Is it angular acceleration equals linear times the radius? Flip.
Flip it.
Linear equals angular times the radius?
Yeah.
Is that
Remember, V equals omega R, A equals omega alpha. I'm sorry, try that one again, alpha R. So this becomes negative L, which is my radius, times alpha.
Where does the negative come from?
The negative comes from, and it's a question of what point you actually bring it in, but angular acceleration, I have it right here, and it's going to start accelerating like that. So my acceleration is out, using the right hand rule. Theta, on the other hand, is this way. Theta is into the word. So theta and alpha are in opposite directions. That's where the minus sign comes from.
You just moved it over to make it easier, because technically theta would be negative in your coordinate.
Yeah, I mean, it's on one side or the other. All right, but I now have angular quantities here, but I still have this issue, the fact that theta is trapped inside the sign. And so, if you recall, or think about it, all this was developed before calculators and computers. It was being done all by hand. Yes, go ahead.
Can you explain why, the acceleration is negative L?
I know that theta and alpha are in opposite directions. That theta, because theta is defined from the vertical, and if that's 0 degrees and I pull it out that way, my angle in terms would be into the board. Once it starts accelerating, it's going to accelerate in that direction like that, out of the board. So they're opposite directions. So I introduced the small angle approximation. If theta is much less than 1. Notice I have no unit after the 1, so we're talking about radians. So if it's much less than 50-something degrees, then sine of theta is approximately equal to the tangent of theta, which is approximately equal to theta. We are talking in radians. If you have your calculator, try it out. Make sure you're in radians and see the sine of 0.1 is approximately equal to 0.1 in radians. And see if I have it in this one. This my book. So I did a plot here of sine theta, tangent theta, and theta itself. And I'm trusting your young eyes can see it. The blue line is the tangent of theta. The green line is sine of theta, and the red line is theta itself, or x in this case. But notice that they overlap quite a bit in this region right here, up until the angle is, well, that's 0.2 radians right there. So they're very much overlapped up to 0.2 radians. Matter of fact, you're 10% off at 61 degrees. Oh, no, wait, that's if you went to the more complex form. You're 10% off at 44 degrees for sine and theta. So if I pull this pendulum back and I just pull back just a little bit, this equation right here becomes something much more manageable. Then it becomes g theta. Now let's go for a different color. G theta is equal to negative L alpha. And we now have it in the Hooke's law form, where we have some number times a position is equal to negative of some number times an acceleration. If we parallel that, because we had negative k delta x is equal to ma, and over here, never said you want to put the minus sign on, we have g theta is equal to negative L alpha. Well, we have this direct parallel there. So the period of the ideal spring was 2 pi square root of m over k. The period of the simple pendulum would be 2 pi square root of, instead of mass, it is length, instead of k, it is g. This, far more than the coil, was something easily done by Galileo, and we now have a timing device. If you know acceleration due to gravity, you can predict how long it needs to be in order to have a period of 1 second. Which means that you've got precision down to 1/4 of a second, because I know in a quarter, if my period is 1 second, in a 1/4 of a second it'll be at the bottom, half second, 3/4 of a second, 1 second again. And this one, we really don't have to take into account the mass of the string, as long as the string is somewhere there. As long as the string is small mass compared to the mass that we have hanging on the end. Thought there was a loop in the edge here. Make that part need. All right, so let's do timing, then we'll figure out what it should be. Stop.